All right, let's kick off this deep dive. We're going to be exploring self-healing systems today. Those systems that can actually find and fix their own problems, which is pretty mind-blowing when you think about it.
It is, especially with how complex these systems are getting.
Yeah, and it's interesting you say that because one of the articles is from vfarsic.github.io, actually compares software systems to the human body.
Ah, yeah, that's a good analogy.
It is. Like our bodies can fight off infections without us even thinking about it.
Right, and self-healing systems kind of try to do the same thing for software. Take Kubernetes, for example. It can automatically restart containers if they fail.
So that keeps everything running smoothly without someone having to, like, manually jump in and fix it every time something goes wrong.
Exactly. I mean, you can't really do that anymore as these systems get more and more complex.
Not to mention that hands-off approach probably saves a ton of time and money, too.
Oh, absolutely. Less downtime, less need for IT staff to constantly be putting out fires.
And speaking of real-world stuff, some of the big tech companies are already using these self-healing principles. The Ultimate Guide you sent over talks about how Netflix uses Chaos Monkey.
Oh, yeah, Chaos Monkey.
They basically use it to intentionally introduce failures into their systems.
Sounds kind of crazy, but I guess the idea is to make sure their systems are super resilient.
Yeah, they basically create a little bit of chaos to see how their systems react and adjust their self-healing mechanisms accordingly.
Which is a pretty interesting approach, and it seems to work for them.
It does. And it's not just Netflix. That same Ultimate Guide mentioned that companies like Google and Amazon are using AI to try and prevent cloud outages.
So they're taking a more preventative approach, huh?
It sounds like it. But the cool thing is, these concepts aren't limited to just software.
Right. We see them popping up in networks and databases, all sorts of places.
It's really becoming a standard, which makes sense when you think about it. And that Ultimate Guide you mentioned actually does a great job of breaking down the core principles.
Oh, yeah, the fault detection, isolation, and recovery.
Exactly. And the way
What?
they explain it is so clear. It's like detective work, quarantine, and first aid all rolled into one.
I like that analogy.
It really helps to visualize how these systems actually work. And then, you've got those design choices that play a key role. I'm talking about redundancy, failover mechanisms, load balancing. Both the Geeks for Geeks article and the one from Microsoft Learn talked about them.
Yeah, they're all super important. Redundancy means having backups in place. Failover mechanisms redirect traffic if something goes down. And load balancing, well, that keeps everything running smoothly by distributing the workload.
So you're not putting too much stress on any one part of the system.
Right. It's all about building systems that are designed to handle failures and disruptions, not just react to them.
That makes a lot of sense.
Mm.
But I'm also curious about the different levels of self-healing.
Ah, yeah, like how these principles are actually implemented, right?
Yeah. The vfarsic.github.io article dives into that concept, mentioning things like retry logic, circuit breakers, and the Akka framework.
Okay, well, let's break those down a bit. So at the application level, you've got retry logic, which is basically just trying an operation again if it fails the first time.
Okay, so it's like when a door's stuck and you give it another push.
Exactly. Then you have circuit breakers. Think of them as a safety mechanism that prevents a failing service from getting overwhelmed.
Like a fuse that blows to protect an electrical circuit.
Exactly. And then there's Akka, which is a framework that's really good for building these self-healing systems. It helps manage the life cycle of these independent units of computation called actors.
So it's like having a bunch of little workers that can operate on their own and even recover from failures without bringing down the whole system.
That's a good way to put it. And then we move up to the system level where we're talking about things like monitoring services, making sure they're responding, doing those TTL checks, and even scaling resources up or down based on demand.
It's like the system as a whole can adapt and heal itself, which is pretty incredible when you think about it. But I'm also curious about the hardware level. Like, can a self-healing system actually fix a broken hard drive?
Well, that's where the limitations come in. At the hardware level, it's more about having strategies for dealing with those failures rather than actually repairing the hardware.
So it's not about physically fixing a broken part, but more about making sure the system can keep running even if a piece of hardware fails.
Right. Like if a server crashes, the system can automatically move everything that was running on that server to a healthy one.
So the services stay up even though the underlying hardware has failed.
Exactly. It's a clever way to handle those kinds of situations.
It really is. There's so much more to self-healing systems than I initially realized.
Oh, we've just scratched the surface. There's a whole world of strategies and techniques for building these systems, and we're going to dive into all of that in the next part of our deep dive.
Can't wait. This is already so fascinating. I'm really eager to learn more about how these systems are designed and implemented in practice.
Well, in the next part, we're going to shift gears and really get into the nitty-gritty. We'll explore specific design patterns and tools and see how these concepts are being used in real-world applications.
Awesome. Looking forward to it. So last time we talked about what self-healing systems are and kind of why they're becoming so important. Now I'm thinking, let's get into like the nuts and bolts of how they actually work.
Yeah, let's shift gears a bit and talk about how to actually build these things.
Okay, cool, cool. So where do we even begin?
Well, it all starts with understanding how to design systems for resilience, right? It's not just about fixing problems, it's about building things that can withstand those problems in the first place.
So like instead of just patching up cracks, you're building a house that can withstand an earthquake.
Exactly. And that's where redundancy comes in. That ultimate guide we talked about, it really emphasizes that.
Oh yeah, redundancy. Having backups like a spare tire or a generator just in case.
Right. And then there are failover mechanisms. They ensure that if one system goes down, another one can take over seamlessly.
Right, which is super important in keeping things running. And then we can't forget load balancing either.
Oh, yeah. That's key for distributing traffic across multiple servers and making sure that no single server gets overloaded.
The Microsoft Learn article had a good section on that, if I remember correct.
It did. So it's all about having backups, redirecting traffic smartly, and spreading the workload effectively. But the question is, how do you actually put these ideas into practice?
Yeah, what are the tools and strategies that people use to build these systems?
That's where design patterns come in. Think of them like blueprints for solving common problems in software engineering.
And there are specific ones that are good for building self-healing systems, right?
Absolutely, like the circuit breaker pattern, which, if I remember correctly, the self-healing systems source talked
Oh
about.
yeah, the circuit breaker. That sounds intriguing, but I don't really know what that means.
Well, think about it like a circuit breaker in your house, right? If there's a power surge or a short circuit, the breaker trips to prevent damage to your appliances.
Oh, I see. So it's like a safety mechanism.
Exactly. The circuit breaker pattern does the same thing in software. If a service starts failing, the circuit breaker trips and stops any more requests from hitting that service. This prevents the problem from spreading to other parts of the system.
That's a smart way to contain those failures.
It is. And then there's the bulkhead pattern, which is similar in that it isolates different parts of the system. That self-healing system source compared it to dividing a ship into separate compartments.
Ah, so if one compartment floods, the whole ship doesn't sink.
Exactly. It's all about preventing a failure in one part of the system from taking down the whole thing.
Got it,
Yeah.
got it. So those are two pretty important patterns, right?
Yeah,
Yeah.
they're really essential for building resilient systems. And then there's the retry pattern, which is more about dealing with temporary glitches.
Oh yeah, like when you try to open a door that's stuck and you just got to give it a few more tries.
Yeah, exactly. And there's this cool library called the Poly Project. I read about it in that Strategies for Building Self-Healing Software Systems source.
Yeah, Polly, what does it do?
Well, it helps developers implement these common patterns like retry, circuit breaker, and bulkhead more easily. It takes care of all the complicated stuff so developers can focus on other things.
So it's like a toolbox that makes building these systems a lot easier.
Yeah, pretty much. We've been talking a lot about these patterns for handling failures and retries and things like that, but there are also patterns for managing the overall behavior of the system, right?
Right, like how everything works together and interacts with each other.
Exactly. One that's especially important for complex systems with multiple components is the supervisor pattern.
Okay, the supervisor pattern. Now that one sounds familiar. Remind me of where we saw that.
It's used in systems like Akka, which we mentioned before.
Akka, right.
Yeah.
I remember that from earlier, but remind me, what is Akka?
So in Akka, you have these independent units of computation called actors. Each actor is responsible for a specific task, and they communicate with each other to get things done. The supervisor pattern defines a hierarchy of actors, kind of like a management structure.
So there's like a boss actor who's in charge of a bunch of worker actors.
Exactly. And the boss, or the supervisor, is responsible for monitoring the worker actors and making sure they're doing their jobs properly. If a worker actor crashes or encounters a problem, the supervisor can step in and either restart it, stop it completely, or even escalate the issue to a higher level supervisor.
So it's like having a manager who's making sure everyone's on track and dealing with any issues that come up.
Precisely.
Hmm.
It's a really elegant way to manage complex systems and ensure that they can recover from failures gracefully.
And speaking of complex systems, what about distributed systems? Those are systems that are spread out across multiple machines, right?
Mm.
Are there any patterns that are particularly useful for those?
Definitely. One that comes to mind is the leader election pattern. It's all about making sure that in a distributed system, there's always one node that's in charge, or the leader. That way, there's no confusion about who's making decisions.
And the self-healing system source mentioned that this pattern is really important for keeping things consistent in those distributed environments.
Right. It helps ensure that everyone's on the same page, which is crucial when you're dealing with data that's spread out across multiple machines.
So we've talked a lot about design patterns and tools, but haven't really touched on AI and machine learning. I'm curious, how are those technologies being used to make these self-healing systems even smarter?
Oh, that's where things get really interesting. AI and machine learning are bringing a whole new level of intelligence to these systems, like being able to predict problems before they even happen. The self-healing application source has a great section on that.
Predicting problems, that sounds amazing. Tell me more about that.
It's called predictive analysis, and it involves using historical data to identify patterns that might indicate a future problem. It's like having a crystal ball that can tell you what's going to break before it actually breaks.
That's so cool, but how does that actually work? How can a machine predict the future like that?
Well, you can train machine learning models on massive amounts of data that's been collected over time, like performance logs and incident reports, and those models can learn to recognize those patterns.
So it's like teaching a computer to be a detective, but instead of solving crimes, it's solving system failures.
Exactly. AI can also automate a lot of the fault detection and recovery processes. Instead of relying on humans to figure out what's wrong and how to fix it, AI can take over those tasks and do it much faster and more accurately.
That sounds incredibly powerful, but it also makes me wonder about the risks. What happens if the AI makes a mistake? What if it misdiagnoses a problem or applies the wrong fix?
Those are valid concerns, and it's why it's so important to use AI responsibly and to make sure that there are safeguards in place. AI should be seen as a tool to augment human intelligence, not to replace it completely.
So it's about finding the right balance between automation and human oversight.
Absolutely.
Yeah.
And even with all the advances in AI, building and deploying these self-healing systems is still a really complex endeavor, especially when you're dealing with legacy systems that weren't designed with self-healing in mind. The self-healing code source mentioned that.
Oh yeah, legacy systems. Those are the older systems that have been around forever and are often really hard to change.
Exactly. Trying to retrofit those systems with self-healing capabilities can be a real challenge.
And even if you manage to build a self-healing system, there's always the risk that it might not work perfectly, right? Like, what if it triggers a false alarm or misses a real problem altogether?
Yeah, those false positives and false negatives can definitely happen.
And the consequences could be pretty significant depending on the system.
Right. A false positives might lead to unnecessary downtime, while a false negative could let a real problem escalate into something much worse.
So it's a delicate balance.
It is. And another thing to consider is the resources that these self-healing processes consume. They need CPU time, memory, and network bandwidth to do their jobs.
So if you're not careful, those processes could actually start to slow down the system they're supposed to be protecting.
Exactly. It's all about finding the sweet spot where the benefits of self-healing outweigh the potential drawbacks.
Okay, so let's say you've built your self-healing system and you've taken all of those factors into account. How do you actually make sure that it's working as intended?
Testing, testing, testing. You absolutely have to put the system through its paces and make sure that it can handle all sorts of scenarios.
So like simulating different kinds of failures and seeing how the system responds.
Precisely. The self-healing application source really stressed the importance of rigorous testing, including unit testing, integration testing, and stress testing.
And those are all different levels of testing, right? Like unit testing is for individual components, integration testing is for seeing how everything works together, and stress testing is for simulating those real-world conditions.
Exactly. And even after you've deployed the system, you can't just assume that everything is going to be fine. You need to constantly monitor it and make sure that it's still working as expected.
So it's not a set it and forget it kind of thing.
Definitely not. Ongoing monitoring and maintenance are crucial. Tools like Prometheus and Grafana are really useful for that. They let you track key metrics and visualize the health of the system in real time.
So you can see at a glance how things are performing and spot any potential issues early on.
Right. And whenever there's a failure, no matter how small, it's important to do a post-mortem analysis. That self-healing application source talked about that.
A postmortem, like an autopsy for a software system.
Kind of. It's about digging deep into what caused the failure and figuring out how to prevent it from happening again. It's all about learning from your mistakes and constantly improving the system.
So it's a continuous process of improvement.
Absolutely.
Yeah.
Building self-healing systems is not a one-time thing. It's an ongoing journey of learning, adapting, and making things better.
This has been super insightful. We've covered so much ground, from design patterns to testing strategies to the role of AI. It's incredible how much goes into building these systems.
And we're not done yet. There's still so much more to explore, especially when it comes to the future of self-healing
Oh
systems.
yeah, I'm really excited to dive into that. Like, what's next for this field? What are the emerging trends and technologies that are going to shape the future of self-healing systems?
Well, that's a perfect segue into the final part of our deep dive. We'll look at some of the cutting edge stuff that's happening and see how these concepts are being applied in new and exciting ways.
Sounds good. I'm ready to see what the future holds. Okay, so we've talked about what self-healing systems are, how to build them, all that good stuff. But now I want to look ahead. What's next? What's the future look like for this whole self-healing thing?
Well, think about a world where systems can practically take care of themselves.
Yeah.
Like they can adapt and evolve on their own. That's where things are headed.
Yeah, and the self-healing code source kind of touched on this, talking about how the Internet of Things is going to make self-healing even more important.
Exactly. I mean, think about it. We're connecting more and more devices every day. Smart homes, smart cities, it's all happening.
And all those devices need to be able to work reliably without someone having to constantly check up on them.
Right. It just wouldn't be feasible to manage all of that manually.
So self-healing becomes crucial in the IoT world.
It does. And it's not just about convenience either. The self-healing system source talked about how these concepts are being applied to critical infrastructure like power grids and even medical devices.
Wow, yeah, that's some serious stuff. And it makes those ethical considerations we talked about earlier even more important, right?
Absolutely. We're giving these systems more and more autonomy, especially in areas where human lives are at stake. We need to be really careful about how we design and deploy these systems.
Yeah, it's not just about making systems that work. It's about making systems that work responsibly.
Right. And part of that is recognizing that AI, as amazing as it is, isn't a magic solution.
So we can't just hand over the reins completely and expect everything to be fine.
Exactly. We need to have checks and balances in place. Human oversight is still crucial.
So it's about finding that balance between AI and human intelligence.
It is, but you know what's interesting? The more sophisticated these systems get, the more our roles are going to change.
In what way?
Well, the self-healing code source talked about how we're going to need people who can design, oversee, and refine these AI-powered systems.
So instead of being replaced by AI, we'll be working alongside it.
Right. We'll need people who understand AI, software engineering, the whole nine yards.
And probably people who can explain all of this to the rest of us, right?
Yeah.
Because this stuff can get pretty complicated.
Yeah, communication is going to be key. Making sure that these systems are understandable, that they're aligned with our values, that they're being used ethically, all of that.
It's like a whole new set of skills we're going to need.
It is. It's a really exciting time to be in this field, honestly. There's so much potential.
It really is. Well, this has been an amazing deep dive. Thanks for sharing your expertise with us. I feel like I've learned so much.
My pleasure. It's been a great conversation. And hey, to everyone listening, remember, technology is constantly evolving. It's up to us to keep learning, keep asking questions, and keep pushing the boundaries.
Yeah, that's what it's all about. Curiosity, exploration, all of that. So thanks for joining us on this deep dive. We'll see you next time.